Hi everybody. Today what we're going to be going through is some basic matrix transformations. But to me, one of the most important things that is crucial to understand for any level of matrix transformation is how to multiply them. So this may seem like a basic skill. It is a basic skill once you learn it, but it is essential for you to actually do the problems that are included here. So with that, let's have a look at some background information. All right, so what you see on the screen is a reminder of some things that are important with matrix multiplication. So matrix multiplication is only defined when the number of columns in the first matrix and the number of rows in the second matrix are the same number. Otherwise, the answer here, which will be, let's call it C, will not be able to be defined and will not exist. So that means A times B will be undefined if this does not hold true. Okay? So that's one thing to hold in mind. So make sure when you're asked about, oops, why did that show up on the screen? So when you multiply matrices, we have to make sure that these two numbers are the same. So once you have established that, another thing you can notice is that the number of rows in the first matrix and the number of columns in our second matrix will end up being the dimensions of the product. So the number of rows in our first matrix and the number of rows in the product will be the same. Also, the number of columns in the second matrix will be the same as the number of columns in our product matrix. So it might seem a little bit obvious to a few of you, but obviously if I'm defining that many things based on what happens in the first and second matrices, obviously this doesn't commute. So order matters. So A times B does not equal to B times A. So that's very important. Make sure you have this in order. All right. So with that said, and the technical difficulties hopefully solved, let's move on to a specific example of this. All right, so if we have a look at our ultimate goal for today, it's going to be looking at how 2x2 matrices transform vectors in the R2 vector space, so real vector space. So how to evaluate for our output, we will have to do a lot of matrix multiplication between a 2x2 matrix and a 2x1 matrix, which is also a column vector with two rows, sorry. So let's have a look at a generic form of this. All right, so if you have a look at the screen, we have a generic 2x2 matrix on our screen being multiplied with a vector in R2, which will give us another vector in R2 that has been transformed. You'll notice that the number of columns in our first matrix is, what are columns again? 1, 2. And the number of rows in our second matrix, 1, 2, are the same, which means that our product will be defined. So then we have this is going to be real. And also, if we look at the number of rows in our first one and the number of columns in our second one, so we have 2 rows in our first one and 1 column in our second one. That means that our product has 2 rows and 1 column. All right, so let's have a look at how this happens. So let's move xy to a different spot on the page. X prime and y prime, that is. All right, so I moved it there so we can actually look at how we evaluate for each of our top and bottom numbers. So let's have a look. So, you may notice in people that do linear algebra a lot that they use x1 and x2 all the way to xn. But since our goal here is to basically just work with stuff in R2, and we're used to working in R2 with x and y, we're just going to use x and y, the original x and y, and then x prime and y prime to make it easier for us to grasp this. All right. Okay. So when we multiply matrices, we have to take each row at once and multiply it by each column at once. So since there's only one column, we only have to repeat this once. So what we do, so if we have a look at our product, oops, it's going to be a 2x1 matrix, and I'm just going to make it a bit wider, even though it's going to only have one column. So the first number is going to be made out of the first row times the first column. So what that's going to be, we're going to take this number and multiply it by this number. So we'll have, we will have the first number in our first row times the first number in our first column. Then you're going to add this. So obviously this is more mechanical than a formula, so don't just write this down as a formula unless you're really screwed and really need to do it like that at this point. So then you add the second number in our first row times the second number in our first column. So that would give us by. So that finishes our first row because there is only one column in our factor there. So if there were more columns in here, we would have to, each column times this row would give us an extra number here. That's how this ends up being true. But first we're just gonna focus on this little one right here. Okay, so what we have, since now we're done multiplying the first row by the column, we're going to move on to multiplying the second row by the column. So in the same way, what we get is we get the first number in our second row times the first number in our first column. So that would give us cx, and then you would take your second number in your second row times the second number in your first column, which would give us plus dy. So really what this is, you just take this, you take each number, this number, you take so to apply this to the even bigger ones, you'd go this number times this number, first times first, add, second times second, third times third, blah, 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 until you're done. Obviously, there's only two here. And then once I finish multiplying every number in this row by this column, you would move on to the next column. And, well, there's only one column. However, once we're done our columns, we're going to start all over again with our next row, and then multiply that by each column. And then do that for each row until the end of the matrix. All right. So now that we have this relationship, we're going to apply that towards some basic transformations. Using 2x2 matrices. So we're going to start with we're going to start off with a pretty easy one, and that's going to be the zero transformation. All right, so what you see on the screen, I actually haven't put anything up on the screen except for the relationship we just described. So we're going to apply that to different kinds of matrices. So the first one is our zero transformation. It is one to get our output oops, we have to multiply a 0 matrix by an input vector to get our new vector. So what our new vector would look like if we multiplied the matrix. So let's go ahead and do that operation. So what that gives us, we're gonna get our first number, this number times this number, to get 0x. This plus, we're gonna add this number times this number, so that's 0y. And then now that we're done with our first row, we're going to move on to our second row. So you have this number times this number, which will be 0x again, and then 0 times this is another 0y. That obviously gives us a 0 vector. So for any input you put into this, so this could be a point. Let's say you had a point anywhere here with x and y anywhere on the thing, it would get transformed to the origin. That's why this is called the 0 transformation. So this doesn't just work in R2 if you keep, but we are only doing this in R2 so far. So any point on your xy plane, if you apply this transformation, you would get every point would go to the origin. That's why it's called the 0 transformation. So we're going to work on a few of these, but the first one is the easy one, just to make them all 0. But we're going to have a look at some where some are 0, some are not 0. But the first one we're going to do, so obviously when we teach people multiplication with normal numbers, we teach people that multiplying by 1 gives you the same, and multiplying by 0 gives you 0. So we did the 0 one. And in matrix multiplication, or just with matrices in general, when you multiply something by something that gives you, that gives you the same something. Like if I took something, multiply it by another thing to give me the same thing, there's a special kind of matrix that performs that, and that will be the identity matrix. So the second one we'll be looking at is the identity transformation. All right, so let's go through with our identity transformation. So our output, I'm just going to write it as x prime, y prime, is going to be the identity matrix for a matrix with 2 rows, 2 columns, which will look like that. And then we'll multiply by a generic input to give us an output. So when we multiply this, what we're going to have, so we're going to have the first number. I don't know what color to use anymore. I don't really care. So we have our first number in our first row times the first number in the first column. We 1x. We're going to add second number, second times second. Oops. That looks like a 1. A second times second is 0 plus 0y. And then we're done with our first row. We're going to move on to our second row. We have our first times our first, will be 0x. And we're going to add the product of the second times the second, which will be 1y. And if we simplify this, we get x and y. And we notice that our input was the same as our output when we transformed it by the identity matrix. Which shouldn't be really a surprise, because multiplying by the identity matrix is basically like multiplying by 1. So if we have an example, if we had 0 times some random numbers, we would get first times first plus second times second, first times first, second times second. You would get the same original numbers. So what that looks like graphically, if you had a point here, which would be represented by a vector as well, you multiply it by you multiply it by the identity matrix, this would get the same thing. You would get the exact same thing. So that's shown there. If you multiply by the identity matrix, you get the exact same thing. It doesn't move anywhere. However, we can change the numbers in our identity matrix, and then we're going to look at how changes in each number have different effects on our input vector, on our output. How it affects our input differently to get a different output. That's what I meant. So we're going to look at how each of these affects this specifically to see what that gives us. Okay. All right, so we're going to start with a horizontal stretch. But before we begin, I would like to stress once again that these aren't like formulas that you should be memorizing unless like you really don't know what you're doing. These are just relationships that are just affected by how matrix multiplication works. So just know how to multiply matrices, as that's just like useful outside of this context as well. And yeah, so just basically just don't memorize these. I'm just trying to show you how this changes. So what I'm going to do is change each number in our identity matrix one by one, like one at a time, to see how this affects that. Okay, so what we're going to do is we're going to change. Oops. We're going to change our first number in our first row to, let's say, a 2. Okay. So, sorry about that. So, and we're going to see how this gets affected in our output. So our output is going to be a tiny bit different. Okay. So, let's go ahead and see what those effects are. So, what that's going to give us, okay, so that's actually written in the wrong order. Let me fix that. All right, so now that we have it properly, let's see what we can do. So to find our output, I don't know why that scrolled. To find our output, x prime and y prime will be equal to this matrix times our input. So we're going to take this, our first times our first will be 2x, our second times our second will be 0y, and in our second row, the first times the first will be 0x plus 1y. I'm going to try to match the color, sorry. So what that gives us, if we simplify, we have 2x and 1y, sorry. So if we look at our input and our output, the x coordinate, if we think about this in a Cartesian manner, our x coordinate will be twice away from the origin as the original. So if we apply that to our example, if we have this matrix times some random numbers, this gives us our first times our first gives us 12. We're going to add our second times second, and then our first times first will be 0 here, and then 7. So then this will give us 12, 7. So we notice with our original, our original x value is 6, and then our output x value is 12. So what this looks like, you can probably visualize this by yourself already, but we have our plane in R2. We are 6 to the right and 7 up. Actually, that'll be about here. That will be transformed to give us 12 to the right and 7 up. So obviously, it's not really to scale, but we can see that this has been horizontally stretched by a factor of 2. So In linear algebra, every point is a vector. So if you look at this, our vector has been stretched horizontally by a factor of 2. Oops. Let's pause. All right. So another thing I can bring up here is that let's say we're not just creating the vector. Let's say we create a rectangle here. So this one would be a 6 by 7 rectangle, and then this would be a 12 by 7 rectangle. So what we're going to look at, so if we take the determinant of our transformation matrix, so I wrote it here. So if I have the determinant, where am I going to write this? If I have to take the determinant of our transformation matrix, remember that our straight brackets means the determinant of whatever's inside. Matrices can be square brackets or curved brackets, and it means just the matrix. However, the straight lines means determinant. And since this is a diagonal, we can just multiply the products along this diagonal. So 2 times 1 is 2. So if we look at the area of the rectangle created by the matrix, if we extend those lines down, the area of this one will be half of what the new rectangle is. So obviously with some of these pretty easy numbers, we can see that the area of this rectangle will be 42, and the area of this rectangle will be 84, and we know that 84 divided by 42 is 2. Now, what we can notice is I notice that the determinant of my transformation matrix, the determinant is the same as the multiplication factor of the area of that rectangle created. So if I have a look, let's say the vector is like when you buy a TV or any kind of device with a screen, and it tells you how big the screen is. So that's where this rectangle comes from. So the area of the rectangle, since the determinant of the transformation was 2, that means that the area increased by a factor of 2. So I multiply this area by 2, I would get the area of the transformed the area of the rectangle that was a result of the transformation. So that wasn't the best way to put that, but hopefully we can see that as well. If I have a look at our identity matrix, obviously the determinant of that matrix was 1, and we notice that the area of this rectangle was exactly the same, because that's kind of obvious because this was the exact same vector. So since the determinant of this 1 times 1 gave us 1, then the area of this rectangle was multiplied by 1 to give us the area of this rectangle. So that's one property we can keep in mind as we work through. All right, so right after doing a horizontal stretch, we can work on our vertical stretches. One last thing I would like to add on right before we move on. Let's say, so a horizontal stretch is defined as let's say a transformation with an identity matrix. However, we have changed the first number in the first row to be t. So t will have an effect on this and shift it horizontal, or stretch it horizontally. Stretch it. So just like when we worked with functions like algebraic, or I don't know what they're called, but the ones you work on in calc and pre-calc and whatever. So when this the horizontal stretch factor is greater than 1, the thing being transformed will get wider, or it will be extended, stretched horizontally, and it'll have a larger width. And then the if I stretch it the other by a factor that is less than 1, oops, but greater than 0, oops, so if it will make this have a lesser, oops, sorry, it'll make this have a lesser x value, so then it would get not as wide. And if I take the determinant of this matrix, I would get t. So t, your area, the area of this rectangle would be multiplied by t, and then it would get bigger or smaller. The area would get larger or greater or lesser, depending on whether t, the stretch factor, is greater or lesser than 1. But it must be, we'll just look at the positive ones for now. All right, so we're going to move on to our vertical stretch. We're going to go through a little bit quicker so that I don't take too much of your time. So let's say that our output is going to be equal. We're going to be changing, so we're multiplying this from the identity matrix. So we remember that when we used our identity matrix, the whole thing stayed the same. When we changed one of the ones that was multiplied by the x directly, it made it be stretched horizontally. So I'm going to change the other number 1 in our identity matrix. Sorry about that. So let's make this number a 2. So let's say we have our identity matrix, but with a 2 here instead, and we have our input. So in our output, we would have the first times first, second times second of our first row. So first times first plus 0y, and then our second times second, or second times second, and our first times first of the second row, so 0x plus 2y. So what that would give us as our output of our function, we would have x and 2y. So obviously our vertical component will be stretched by a factor of 2. So what that would look like, let's say we had this matrix 1, 2, 0, 1, 0, 0, 2 times 3 and 4. We would get 3 times 1 times 3 plus 0 times 4, which will be 3, 0, and then our second row in our output will be 0 times 3 plus 2 times 4, which is 8. And notice our vertical component has been stretched by a factor of 2. I notice if I draw this out, that if I have this, if I apply the transformation, I would get let's say about there. So obviously this isn't the scale, but whatever. So, and I notice if there is a rectangle, being here, if I have a rectangle here, that area has doubled, and then also the height of the rectangle has doubled. So this may come in handy. You might be given a picture. You might be given this, and then be asked to find what the output looks like, or you might be given you can be given any combination of whatever's on the screen right now. You'd be given the input and the output, and you'll be asked to find this. And we've already covered this in a video. And then depending on which we covered, like really complex examples that did not have a picture in it. So you could be given just the input and the output in even in x and y form, and then be asked to find this, which I just mentioned we covered before, without pictures. But you could also be given these inputs and outputs with being labeled on the diagram, and you could be asked to find it using the pictures. But the pictures will also be giving you the coordinates. So I'm going to clean this up before I move on. And once again, if we take the determinant of our transformation matrix, we get 2. That's how this was, sorry, let me get my pen back out again. So, so the area has doubled because our determinant was 2. So, the general form for this, once again, let me switch my pen back. So this would be our identity matrix, but with, so the number here that gets multiplied by the y value of our input directly is the one that gets changed as our stretch factor. So then, so some people call this a stretch and a compression, but that doesn't really matter. So this one, if I input a square, I would get a tall, I would have my height changed if I had a stretch factor that was greater than 0 but less than 1. That would be that the square would get squashed but still have the same width. All right, so we're going to look at a few examples where we change the zeros around. So this is going to get a little bit more weird because if I change the zeros, I notice that the zeros aren't the 0 here is part of the output here, but it's not multiplied by my x value. It's going to get multiplied by my y value, but it still affects my x value of the result. So we're going to have a look and see how that happens. All right, so as I just discussed, or I don't know what word to say, we're going to be changing this number from our identity matrix. So if you were given, so let's say we're starting with our identity matrix, but we're changing that number. So our output, x prime, y prime, can be given by our identity matrix, but we changed this number. So let's make it, do I just keep using 2? Let's just keep using 2. So let's just do 1, 1. So our square, let's do a square, just 2, 2. Actually, we'll go 3, 3 because we already have some 2s and 3s here. So actually, I was going to do a generic form. So let's go back to x and y. I apologize for the erasing. So we multiply this. I have 1x minus or plus 2y. And then in our bottom number, we have 0x plus 1y. And then that gives us x plus 2y. And 0x plus 1y will be y. So obviously this isn't as simple as before. So this is more of a shift. However, it's shifting only one set or one component of our resultant output thing. So vector, that's the word. So what that would look like, our basically x and y is about the same. However, what do I want to say here? So x and y stay the same. So we have an x and y in our output. However, our x1 will have a multiple of y added to it every time. So let's see how that looks like. So what are we going to do? So okay, let's try. So our output for this transformation with, let's use 3 and 3 again. So we will have first times first, which will be 3. We're going to add 2 times 3. 2 times 3, we'll add 6. And then we'll have in our second row, we'll have 0. We're going to add this times that will be 3 again. So this will be 9 and 3. So if we look at this, this follows the rule. We have we are inputting 3 and 3. Our output for y is 3. However, our initial x input has added, we've added a multiple of our initial y value to it. So we've added 2 times 3, okay, 2 times y to our x value to give us 9, 3. So what that would look like, so we start off with a square at 3, 3. A square with constructed by a vector at 3, 3. What that would give us, let's say we would have let's ignore the square thing for right now. So we have a 9 and 3. All right, so for the square analogy to work, we're gonna have to look at every corner of the square. So let's see where that takes us. So with our first corner that we looked at, our 3, 3, that gives us a 9 and 3. Oops, why is that 3 so small? Okay, but there are 4 corners to our square. Let's look at how each corner is affected by this transformation. So the initial points in our square, we had 0, 0. We had 0, 3. 0, 3 is up here. And we had 3, 0 down in the corner there. So what I'm going to have you to do, what I'm going to have you do is I'm going to get you to pause the video, and then you're going to do this, but instead of 3, 3, we're going to do each of the other points of the corners of the square. And we're going to see what we get up. We're going to see what we have back. So we're going to pause the video and work through that yourself. All right, pause the video now. All right, and we're back. So hopefully you've taken the time to calculate each of the corners and how it gets affected by the transformation. So if we look at this, let's say we have, we're gonna pick 0, 3 first, and then we're gonna do it in blue. So we have 1, 2, 0, 1 times 0, 3. That gives us, oh, I wrote that really close. We have 0 plus 6, and then we have 0 plus 3. We have a point at 6, 3. So where that is, that's about, I don't know. Wait, 1, 2, 3, 4, 5, 6. Let's put that there. Okay, so that will be at 6, 3. All right, let's do a next point. We'll do it in green. We'll take our 0, 0 and make it green. So we have our 1, 2, our transformation matrix times our input will be 0, 0. We're gonna look at this, and then, oops, that doesn't look good. So I have 1 times 0 plus 2 times 0, which is 0, and then 0 times 0 is 0, and we're going to add 1 times 0 is 0. So surprise, surprise, that point doesn't change. However, let's look at where the fourth point lands up being. So this might be the interesting part. So let's do it in, okay, this point was blue, that point was green, and then let's do purple. So this point is going to be the purple one. So if I take our transformation matrix, multiply it by our input, so we have 3, 0. That gives us our first times first is 3. We're going to add 2 times 0. And then our second row, we have our first times first is 2. Our second times second is 1. Oh, wait. Our second times second is 1 times 0, which will also be 0. And I notice that another point will be the same as our input. So let's look at that. That will be in about the same spot. So it'll be about here at 3, 0. This one is at 0, 0. So I notice that my square has been sheared to look like a parallelogram. So what I have here is, oh no, that's not good. A parallelogram. After I apply this, I have a parallelogram. Let's go back and look at the property where we take the determinant of this matrix and then see what happens. So, okay, let's go. I don't know where I have room for this. So, Let's go. I've set that up a lot. So let's take the determinant of our transformation matrix. So I notice, oops. Okay. So the formula for this is AD minus BC, where A for a matrix A, B, C, D, it's just going to be AD minus BC. So you can look at what spot each of those represent. So if I do that, A times D is 1 times 1, and I'm going to subtract 2 times 1. So that gives me -1.